This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, so a couple points before continue with the lecture. Just had us a few questions. So I talked about monotonicity. Remember we said the more goods is better. But I said in actual practice, often that takes the form of more quality rather than more quantity. That is, maybe instead of buying a cheap car, you buy a more expensive car, a nicer car, one that has a higher quality, right? But in some sense, that's still more of a car, right? Because that better car maybe has air conditioning, whereas your old car didn't. Or maybe it has a satellite navigation, or so on and so forth. So it's more of a car, even though you still only bought one car, right? Likewise, if you stay at a hotel, if you stay at a 5-star hotel versus a 4-star hotel, you're getting, in some sense, more hotel service in a 5-star hotel than you are in the 4-star. Now, we actually have a way of measuring this in applied work, because in applied work, quality differences matter. So what we do is a method, just you don't have to worry about this for this course, but it's a method called hedonic analysis. And basically, you measure all the quality differences between the goods, put a price on those quality differences, and say how much better this good is of a higher quality compared to one of a lower quality. So, for example, we could say maybe the 5-star hotel, one night at a 5-star hotel, is equivalent to two nights at a 4-star hotel. So we convert a quality into a quantity measure, right? So in some sense, one night at a 5-star hotel is more than one night at a 4-star hotel. Right? We have a technique to do this. I just want to let you know. So here's a page from the Australian Bureau of Statistics. Right? They actually have to do this, measure quality change. Why? Because they're measuring consumer price indices. And you don't want your consumer price index to say that prices have gone up for inflation if the only reason the prices have gone up is because you're getting more quality. So for example, suppose there's a car that last year say GM would sell, but it didn't have any air conditioning in it, right? If you bought it, it was an optional, you had to pay $1,000 for it or something. Suppose this year it becomes standard, right? And the price of the car goes up by, say, $800, right? So even though the price has gone up, you have no inflation because you're getting more car, right? And in fact, you're actually saving money. Last year, you would have had to spend an extra $1,000 on air conditioning. Here, you only have to spend an extra $800. So in some sense, the price has actually gone down. All right? So that's what is very important for statistics agencies like the ABS to measuring inflation, is you've got to control for quality changes, right? More is better, is what I'm saying. But usually, it's in the dimension of quality, or often it is, rather than quantity. So if you're interested, go to the ABS and look for the information paper, Introduction to Consumer Price Index, weighted update. Just go to this video and you can get the link at top there. All right? Oh, here it is here. So if you're interested, it talks a little bit about it. So quality change in practice. So it just points out that some goods change more in quality than others. Right? So liquor doesn't change very often in quality. Right? The Johnny Walker Red this year is the same as the Johnny Walker Red last year. By the way, that's a Scotch in case you don't drink. Okay? But other goods do change a lot, have difference in quality. One that I did some work on is housing. Every house is different, right? Even if it's just the location. Even if you build two identical houses, they're not going to be in the same place, right? So every house is different, and somehow we have to standardize them and say this house is worth, 1.5 of another house, right? And since more is better, we prefer that house. Right, so there's ways of doing that. Houses tend to improve over time. If you look at the data, houses tend to get bigger over time, and they tend to have higher quality material on average over time. All right, not always, but on average. Okay, so this just gives an idea that some goods change in quality more than others, so you need to control for it. Right, the biggest example is computers, right, or phones. Right, the phone you buy this year is much higher quality than the phone from 5 years ago in terms of what it can do. And yet the price is the same or even lower. All right? So those are things that ABS has to control for. So anyways, I want to point out that more is better is our assumption. Sometimes that dimension is in quality rather than quantity, but we convert the quality into an equivalent quantity measure and say, well, it's equivalent to having, one night at a 5-star hotel is equivalent to having 2 nights at a 1-star hotel. So 1 night at a 5-star hotel is more than 1 night at a 4-star hotel, right? So just be aware that often in the real world, it's in the dimension of quality rather than quantity. So if anybody's interested in that. Okay. The other thing I want to draw your attention to, someone mentioned, right? We said that, here's our indifference curves. Remember, all the bundles along the same indifference curve are equally ranked. So all the bundles along this blue curve are equally ranked by the consumer. All the bundles along the green curve are equally ranked by the consumer. And all the bundles along the red curve are equally ranked among the consumer. And we said that indifference curves farther from the origin are more preferred, right? By monotonicity, they have more than the ones before. And we use transitivity as well in our argument, right? So we have the red, all the bundles on the red curve are preferred to all the bundles on the green curve, and are preferred to all the bundles on the blue curve, all right? Now what I want to point out is we said, okay, the indifference curves are a visual representation of our preferences, our rankings, right? The red ones are more preferred than the green ones are more preferred than the blue ones. There's our ranking. And remember, this actually fills up the entire space with indifference curves, but I'm just showing 3 of them here. Okay. Then we said, okay, instead of using a visual representation or graphical representation of preferences, we want to do a numerical representation using what we call a utility function. And remember, the only thing that you need to do to make a utility function, it has to satisfy 2 properties. All the bundles that are equally ranked, that is, all the bundles on the same indifference curve, get the same number. So on here, all the bundles on the blue indifference curve get the number 2. All the ones on the green indifference curve get the number 3. And all the ones on the red indifference curve get the number 1 million. All right? The second property it has to satisfy is if it's a more preferred bundle, it gets a higher number. And that's what we've done here. Right? The reds are the most preferred, it gets the highest number. Then the greens get the second highest number. And then the blues get the third highest number. Right? Any utility function that satisfies those 2 properties is a utility function representing that person's preferences. So what I pointed out is that there's no one utility function. Utility functions are not unique. I could have added 5 to each of these numbers and say, okay, now we have a utility function called V. V1 is equal to 7, V2 is equal to 8, and V3 is equal to 1,000,005. Right? That's still a utility function representing this person's preferences, because it satisfies the 2 properties that all the bundles on the same indifference curve have the same number, and more preferred bundles have a higher number. All right? So, but notice here, even though I've changed the utility function from U to V, the indifference curves are exactly the same. They don't move. All I'm doing is changing the number for that indifference curve. Instead of calling it U equals 2, now I'm calling it V equals 7. Right? The indifference curves don't change. That's your preferences. Those are stable. Right? But we can call the numbers anything that we like as long as they satisfy those 2 properties. Okay? So as I said, we could add a constant to a utility function, and that would also be a utility function. Like I said, add 5 to each of the numbers. Or we could multiply by, say, 10. Instead of having 2, 3, 1 million, we could have 20, 30, 10 million. That's also going to represent the preferences. Or we could square them, right? Instead of 2, 3, or 1 million, we'd have 4, 9, and 1 million squared. Whatever that is. Okay? 1 to the power of 12, I guess it is. Okay. All right. And then we said, okay, let's do a few examples of utility functions to get a feel for this. And we said, 2 goods are considered to be perfect substitutes by an individual if they don't distinguish between those 2 goods. From the consumer's point of view, they're identical. So we said in this example, we have 2 goods, X1, X2. The first good are bottles of Mount Franklin water, and the second good is bottles of Evian water. Okay? Now, somebody asked me after class, just to avoid confusion, notice I defined the goods in terms of number of bottles, the bundles in the number of bottles, not in terms of the milliliters. I could have made it in terms of milliliters. I could have said this is milliliters of Mount Franklin water, and this is milliliters of Evian water, right? In that case, you know, if you bought one bottle of Mount Franklin and one bottle of Evian, there would be 500 there. But I did it in terms of bottles, so if you have one bottle of each, this is one is a bundle, okay? It all depends upon what the units you use, okay? Okay, we said we'd only care about the total quantity, right? So we said the way to represent this set of preferences with the utility function is use utility is equal to x1 plus x2. That is, for any bundle, we add together the amounts, the number of bottles, and the total number of bottles is going to be the number that we assign to that indifference curve. All right? So for u equals 2, right, that indifference curve that it gives us utility of 2 will be all the bottles such that the bottles add up to 2. Right? And then we did that last class, and we said here's all the bundles that give you utility of 2. Right? You could have 2 bottles of Mount Franklin and no Evian, 2 plus 0 is 2. Or no Mount Franklin, 2 Evian, 0 plus 2 is 2. Or 1 of each, 1 plus 1 is 2. All right? Or you could a half bottle of Mount Franklin and 1.5 bottles of Evian. That adds up to 2 as well. All right? So all of those combinations, all those bundles on that blue line, right, all give you the same utility, and we're going to assign that utility number of 2. And again, we could have squared this, and that's also a utility function. We could have given this the number v equals 4 and called that a utility function as well. But we called it 2. Changing the number doesn't change the indifference curve. It's still there. Okay? All right. And so just to draw this maybe example, you know, here would be utility of 3. If I can do this. Somewhere like this. Oops, missed a bit. Yeah, you get the idea. You can do better than me. All right? So those are all the combinations that give you utility of 3, right? Those are all the ones where the total number of bottles add up to 3. 3 Mount Franklin, no Evian, 0 Evian, 3 Mount Franklin. Oh, sorry, yeah. 3 Mount Franklin, no Evian, no Mount Franklin, 3 Evian, or 2, 1, 1, 2, 1.5, 1, whatever. All right? Again, indifference curves farther from the origin are more preferred. He'd rather have 3 bottles of water than 2 bottles of water. All right? Again, if we change the utility numbers, that's fine. I could square all these numbers. All the ones along the blue indifference curve, the dark blue, would have a utility of 4 now. So we say v equals 4 for the first indifference curve. The second indifference curve, 3 squared is 9. We give it the number 9 instead of 3. Right? Doesn't change the indifference curves. It just changes the numbers that we give to them. Okay? So don't get caught up in indifference curve, utility numbers. Right? You know, often in things like in psychology or something, you think about, you know, how many utils are you getting from eating that apple? You know, how much happier is it making you? That's not what we're doing here. We're just saying a higher number means you're happier, same number means you're just as happy, a lower number means you're less happy, not how much. Okay? All right. So I have a question here. I'll put this on full screen. I want to try to use the poll everywhere. I do this occasionally. So let me set it active. I think this is how it works. Supposed to say oh, there it is. Okay, so this should activate it. Okay, if I'm right. And then if you go to pollev.com/JamesBugden719, you should see that poll. Or if you want to type a text message to JamesBugden719 at this number, you could also join. Now, the way I've set it up is, I don't know your name. It doesn't tell me who you are. Right? So completely anonymous, completely stress-free. I just want to see if I get some feedback, and I wanted to test it out here. So I tested it out with a relatively simple one. What do you think the margin rate of substitution is for this utility function? Now, it turns out that this one is constant, right, because the slope is linear, right? But what do you think the margin rate of substitution is for this utility function? Now, as you answer, the answers should show up, although it should have shown up properly. It's not showing up properly. But the choices were -2, -1, 0, 1, and 2. And unfortunately, I don't know why, it's not showing up. Let's see if I can get that. Is that any better? Well, there it is. Okay. So there's your answers. I can tell it's anonymous. I don't know who answered A, B, C, or D, or whatever. E, or E, the 5 choices. Okay? All right. There we go. All right. So I'll do this occasionally in the course just to see, get some feedback, see we'll make sure we're understanding what's going on. So just get an idea. All right, so what is the margin rate of substitution? Well, I'll bow to the tyranny of the crowd, and the answer is indeed D. Right? Remember, margin rate of substitution is the negative of the slope. Right? So the slope here is -1. Right? If you calculate the slope of that line, it's going to be -1. So the margin rate of substitution is the negative -1, which is +1. Now this should make intuitive sense. You didn't actually have to do any calculus to do this. Remember, margin rate of substitution says, how much are you willing to give up of the second good to get one more unit of the first good and be just as happy? Now since your utility function is x1 plus x2, right, if I give you one more unit of x1, then you should be willing to give up 1 unit of x2 in order to get that one more unit of x1 and you'll be just as happy. Right? If x1, go back here, right? If x1 increases by 1, you should be willing to give up 1 unit of x2, right? And then you still be just as happy as before, right? So if you had no Mount Franklin and 2 Evian, right? But you give up 1 Evian to get 1 more Mount Franklin, now you have 1 plus 1, you have 1 of each, your utility is still 2, you're just as happy. Right? So you're willing to trade off 1 to 1 here, okay, in that example. All right. This one's a bit more trickier. So perfect substitutes, the 2 goods are exactly identical. This is sort of an opposite case. With perfect complements, you always consume the goods together in fixed proportions. Now an example we're going to do is proportions are 1 to 1. It doesn't have to be that. In fact, I'm going to make a tutorial question where the ratio, the proportion is not 1 to 1, it may be 1 to 2 or 2 to 1. Okay? But it's fixed proportions. Okay? So the idea here is you consume in fixed proportions because any more of one without more of the other doesn't make you any happier. So the classic example is shoes. Right? If you have 1 pair of shoes, yeah, you're happy. If you have 2 pairs of shoes, you're even happier. More is better. 3 pairs of shoes is even better. But if you have 1 left shoe and 3 right shoes, the extra 2 right shoes are useless to you. That's the idea, right? You buy shoes in pairs because there's no point in buying a left without getting the right. Or maybe some people do, I don't know. But that's usually the example, all right? We usually buy shoes in pairs in fixed proportions, 1 each. 1 left, 1 right, okay? So having 1 left, 2 rights, or having 2 lefts and 1 right doesn't make you any happier than having 1 of each. Okay? So think in your mind, what would that indifference curve look like? All right? All right? We'll come to that in a second. But what I'm going to show you is how we can represent those preferences with a utility function. Now this one's tricky. All right? Anyone want to take a guess? All right? Remember, more of one without having more of the other doesn't make you any happier. What does it look like? What's that? X1 equals X2? That's not a function. You're getting closer, but what if I have one left shoe and three right shoes. What's the utility of that? How do I represent that? What's that? Yeah, you're getting the idea now. Okay? The function, anybody wants to guess? Oh. Well, okay. Very good, yes. All right? If anybody hasn't seen the min function, it's easy. It says, look at all the numbers inside the bracket. The smallest number is your utility number for that bundle. Okay? So if you have a bundle x1, x2, put those quantities of x1 and x2 in the brackets. Whatever the smallest of those two numbers, that's what your utility number is going to be for that bundle. Okay? Let's see why that works. Right? If you have one left shoe and one right shoe, right, what's your utility? Well, the minimum of 1 and 1 is just 1. Right? What if you have one left shoe and two right shoes? Well, the minimum of 1 and 2 is still 1. Right? And that represents our preferences. Having more right shoes without having more left shoes doesn't help you, doesn't make you any happier. Right? You're just as happy with one left and two rights as you were with one left and one right. Okay? Likewise, if I put U2, 1, that would also give you a utility of 1. Having two right shoes and only one left shoe doesn't make you any happier than having one of each. But if I put U2, 2, it sounds kind of weird, the bundle 2, 2, the minimum of 2 and 2 is 2. A higher number, you prefer that. 2 pairs of shoes are better than 1 pair of shoes. Okay? So what does it look like? You already guessed what it looks like. Right? Try to draw it on the next curve. I'll put left shoes on the horizontal axis, right on the vertical axis. What are all the combinations that give you a utility of 2? I think I said 2. Yeah. Think about that. Okay. So you're right. Well done. Right? These are all the bundles that will give you a utility of 2. If you have 2 left shoes and 2 right shoes, the minimum of 2 and 2 is 2, so your utility is 2. If you have 2 left shoes, if you have 2 right shoes but more than 2 left shoes, your utility is still 2. Right? The minimum of 2 and say 8, well, I guess it'll be left is first. The minimum of 8 and 2 is going to be 2. Right? Likewise, if you have 2 left shoes and more than 2 right shoes, your utility is 2. The minimum of 2 and 5 is still 2. All right? So these are all the bundles that will give you a utility of 2. Having extras of one without the other doesn't make you any happier. Okay? We call those perfect complements because the idea is, right, you consume them together. You want to consume them together. All right? So left shoes, right shoes. That's why you buy shoes in pairs, because you always want to consume them together. All right? So that's what a perfect complement would look like. Right? And I think I do have it on this one. Okay. Couple of things about this indifference curve. Right? Notice when you want to calculate the margin rate of substitution, anywhere on the, remember the margin rate of substitution is the negative of the slope. Anywhere on the horizontal component, the slope is 0, so the margin rate of substitution is 0. That should make sense. Right? If you're here, say 3 left shoes and 2 right shoes, you don't want to give up any right shoes. Because if you give up any right shoes, your utility goes down. Right? Right's already the minimum. Right? If you're at 3, 2, the minimum of 3, 2, so if you have 3 left shoes, 2 right shoes, the minimum of 3 and 2 is 2. So if I reduce the number of shoes, the right shoes, to 1, now the minimum of 3 and 1 is 1. That'll make you worse off. You're not willing to trade off any right shoes to get another left shoe if you're over here. And that's what it's telling you. The opposite over here, the slope is negative infinity, the margin rate of substitution is plus infinity. Right? If you have extra right shoes, you're quite willing to give up right shoes to get another left shoe because your utility will go up. Right? If you have 2 left shoes and 5 right shoes, and I say to you, give me a right shoe and I'll give you another left shoe, now you have 3 left shoes and 4 right shoes. Now your utility is 3 rather than 2. Right? So you're quite willing to do that. You're very willing to give up right shoes to get another left on that part. The problem is at the kink, at the corner solution, the corner. right? At the corner, obviously no derivative exists. So there is, the marginal rate substitution is undefined there, right? You can have any slope there from infinity to 0, okay? So the marginal rate substitution of that part is going to be undefined. So one of the problems here is, if you have this perfect complement and difference curves, we can't use calculus to solve this one. So if I give you a question on the assignment or something and say, you know, what would the consumer choose if they had this kind of preferences, you can't just differentiate a function and solve, because the derivative doesn't exist there, as we'll see later on. Okay? All right, the other point is, remember, just like normal, right, the further you are from the origin, the indifference curve is from the origin, the more preferred it is. But it doesn't quite satisfy monotonicity. It does weakly, right? I think you notice it says this violates weak monotonicity. What I meant to say is it weakly violates monotonicity, right? So this weakly violates monotonicity. What do I mean by that? It satisfies the first property we said about monotonicity. If you have more of both goods, that makes you happier. 3 pairs of left shoes and right shoes, 3 pairs of shoes, is better than 2 pairs of shoes. Right? That makes you happier. Utility of 3 as opposed to utility of 2. But having 3 pairs of left shoes and 2 pairs of, having 3 left shoes and 2 right shoes is no better than having 2 and 2. So more of one good without having more of the other doesn't make you happier, which it used to, remember? Right? If you have more pizzas and the same number of movies, then you're happier. If you have more movies and the same number of pizzas, you're happier. That doesn't happen here. So it doesn't quite satisfy monotonicity, it sort of satisfies it. Okay? So just to give you a feel for this. Okay. Now, let's use a utility function that we use a lot in economics, and the reason we use it a lot is it has a lot of nice properties. In particular, it's easy to differentiate. Okay? So we use this utility function a lot. It's going to have a lot of nice properties, as we'll see. Okay? We call this a Cobb-Douglas utility function. We're also going to use this functional form on the producer side, as we'll see later on. But this is a Cobb-Douglas utility function. I believe Cobb was an economist and Douglas was a U.S. senator. So I don't know why U.S. senators were doing this back in the 50s, but they came up with this. I think he might have been a former economist. All right. So here's the Cobb-Douglas. So an example of a Cobb-Douglas utility function. What do you mean by Cobb-Douglas? Notice that it's x raised to the power of some fraction, and then y raised to the power of 1 minus that fraction. So x to the 2/5 and y to the 1 minus 2/5, which is 3/5. Right? That's a Cobb-Douglas utility function. In general, we would call it x to the alpha times y to the 1 minus alpha. Right? So the powers add up to 1. Okay. Okay, so let's see why this gives us nice results. At least the first case, why gives nice results. Okay, let's derive the marginal rate of substitution. Now what I'm going to do it the way you're not going to do it. Right, I'm going to do it the long method, right, because I want to show you why it works, and then I'll show you the shortcut method, the way you actually do it, because we're all lazy. Okay, so let's do the long method, and then I'll show you the short method to avoid all this hassle. Okay. So for the long method, what we're going to do is we're going to totally differentiate the utility function, right? So take the partial derivative of utility with respect to x times dx plus the partial derivative of utility with respect to y times dy, okay? And then if you differentiate u, you get du, but remember, along any indifference curve, all the bundles have the same utility by definition. So there's no change in utility as you move along in the indifference curve, so du will be equal to 0. All right? So once you totally differentiate the utility function, you set it equal to 0, and then you can solve out to find the slope dy dx. And then just remember at the end, the marginal rate of substitution is just a negative of the slope of the indifference curve. Okay? So let's see what it looks like, the long method. All right, so this is totally differentiating the utility function, right? du is equal to the partial derivative of utility with respect to x, right? Du dx times dx plus du dy times dy. All right, so let's differentiate the utility function with respect to x. I assume you guys know calculus inside out, probably much better than me anyways. But remember, a partial derivative, if you differentiate with respect to x, you're holding y constant. So treat the y as a constant, like the number 2 or something. All right, so if we differentiate with respect to utility with respect to x, holding y constant, then using the power rule, we take the exponent, the power, multiply it in front, drop the exponent by 1, and leave the y the way it is, right? So the partial derivative with respect to x is going to be 2/5 x, and then we drop the exponent by 1, so instead of being 2/5, we subtract off 1, becomes minus 3/5, right? So that's the partial derivative with respect to x times dx. We do the same thing for the partial derivative with respect to y times dy. We take the exponent on y, we multiply it in front, 3/5, and then we drop the exponent on y by 1. 3/5 minus 1 is minus 2/5, and we leave the x the way it is. Okay? So there's the totally differentiating the utility function. Again, this is the long method that you won't do normally. Okay? And then we say, well, along any indifference curve, du is equal to 0. So we set this equal to 0. And now we can solve out for dy dx, get the slope, the derivative. Don't tell mathematicians about this one, by the way. Right? If a mathematician tells you dy dx, the derivative, is not two quantities, dy divided by dx. Right? It's actually just one thing. Right? But we're not in mathematics. We're going to pretend that doesn't exist. Okay. All right. So this is just saying, what's the slope of the indifference curve? So I don't know. I needed some kind of notation to say we're going along the same indifference curve. So I said, all along the indifference curve, we know the utility is constant. Right? So I said, what's the slope along the indifference curve? That's the way you can just read that. Right? So what's the slope along the indifference curve? That is where the utility is the same. Right? Well, what we do, solve out for dy dx. You can see, move the first term over to the left-hand side, to the right-hand side, becomes minus this, and then divide out by the coefficient in front of dy, and then divide out by the dx, and you get this. Okay? It looks complicated, but notice that this can be solved really easily. Right? 2/5 divided by 3/5 is just 2/3. Remember, if you take a variable with the power and you move it from the numerator to the denominator, or denominator to the numerator, you just change its sign. So if we take x to the minus 3/5, put it in the denominator, it becomes x to the positive 3/5. And remember, multiplying two variables with the same base, you add the exponents. So we have x to the 2/5 times x to the 3/5, which is just x to the 1, or x. Likewise, if you move y to the minus 2/5 to the numerator, it becomes y to the plus 2/5. Multiply by y to the 3/5, add the exponents, becomes y to the 1, which is just y. So notice this really simplifies down to 2y over 3x. So this is one reason why we like using the Cobb-Douglas utility function, is that the margin rate of substitution, which remember is the negative of the slope, is just going to be 2y over 3x. Nice and simple. Right? So if I tell you, if you have the bundle of 5 units of x and 10 units of y, what's your margin rate of substitution? Well, 2 times 10 is 20, 3 times 5 is 15, 20 over 15 is 4/3. That's your margin rate of substitution at that bundle. Right? You're willing to give up 4/3 of a unit of y to get one more unit of x. Right? If x is 10 and y is 5, then we have 10 over 30, which is 1/3. Right? Your margin rate of substitution at that bundle will be 1/3. You're willing to give up 1/3 of a unit of y to get one more unit of x. Right? So it's very easy to find the margin rate of substitution. Now I'm going to show you the easier method instead of doing all of this. Okay? If utility is a differentiable function, so not our perfect complements one, remember it's not differentiable at the kink, but if it's a differentiable function, define the marginal utility of x to be the partial utility the partial derivative of utility with respect to x. Right? What we mean by that is, how much happier are you if you get a bit more x? That's what du dx is saying. Right? Holding y constant. It's a partial derivative. Right? So if I give you a little bit more x, but you have the same amount of y, how much happier are you? That's what this is telling us. That's what marginal utility is. Right? How much happy you are with an additional unit of x. Likewise, and keeping y constant. Likewise, the marginal utility of y will tell you how much happy you are with an additional unit of y, but holding x constant. Okay? Now, the nice short form is, once you calculate the partial derivatives, the margin rate of substitution is simply the ratio of the marginal utilities. The marginal utility of the good that's on the horizontal axis divided by the margin utility of the good that's on the vertical axis. Right? So instead of going through that long form of totally differentiating function, to get the margin rate substitution, just take the ratio of the margin utilities, the ratio of the partial derivatives. Okay? Nice and simple. Okay. All right, so let's see it here. We've already done the work, right? What's the margin utility of x? What's the partial derivative of utility with respect to x? We already calculated that using the power rule. Margin utility of y, we already did that using the power rule. So we just take the ratio of the two, and we get the same answer, of course, 2y over 3x. Okay? So that's how you would do it for this Cobb-Douglas, calculate the margin rate substitution, or for any differentiable function. You just take the ratio of the partial derivatives. Okay? And now you got your margin rate substitution. Nice and simple. You don't have to go through the long method. I want to show you the long method just to show you where this formula comes from. It's not magic. Okay? All right. Just want to show you what this utility function looks like for some bundles of x. Now here's a three-dimensional diagram. Along the base, those are all the bundles of the goods, x and y, right? So, 5 units of x and 2 units of y or whatever. Those are all the bundles on the base of this cube. Okay. The height of the cube represents the utility. Right? So the base is the bundles, x, y. The height is the utility number we attach to that bundle. Okay? Now notice that all these bundles on the base here, along this curve, all have the same height. That is, they all have the same utility. So we know they're all in the same indifference curve. Right? So all these bundles on this curve here, they're on the same indifference curve. So notice that the indifference curve is convex. Right? If you look down from above, you get a convex curve for our indifference curve. Those are all the combinations of x and y that have the same utility, that is the same height here of this function. Okay? Just to avoid a bit of confusion, especially if you have a bit of math background, right? Notice that the utility function can be concave, like it is in this example, but the indifference curves are convex. Right? It's a concave utility function in 3 dimensions, right? But the indifference curves are convex. Okay? So just be careful about that. Sometimes that could be confusing. Okay? So here's what the indifference curve looks like. It's convex. Right? It's bowed in rather than bowed out. All right? So these are all combinations, say, of x and y that give us a utility of 30. Right? That is, looking down from that utility function in 3 dimensions, that's what we'll see. Okay? Nice thing about Cobb-Douglas, why we like using them, they're strictly convex. Now remember what we mean by convex. That says if you take any 2 points on the curve, draw a straight line between them, right? Then all the points in between must be above the curve. That's what we mean by convex. Right? To be concave, if you draw a straight line between 2 points on the curve, then all the points on that line in between will be below the curve. Okay? So this is convex. In fact, it's what we call strictly convex, because all the points on the line in between these 2 points on the curve will be strictly above the function. Right? You can actually have convex functions, not strictly convex, and you don't have to guess what they look like because we've already seen them. Here are 3 convex functions. Right? These are all indifference curves, the ones we saw, the perfect substitutes, perfect complements, and here's our Cobb-Douglas. Right? Perfect substitutes, that's a convex function. That is, if you take any 2 points on the curve, draw a straight line between them, all those points are on or above the curve. Now, they're on the curve, right? But the definition of convex says it has to be on or above. Now, these are all on, so it is convex. It's also concave, right? On or below. So the linear function is both convex and concave. Notice that the perfect competition, revealing my economics again, perfect complements indifference curve is also a convex function. Take any 2 points on the indifference curve, draw a straight line between them. If we pick these 2 points, all the points in between them lie above the curve, so you might think it's strictly convex. However, this has to be true for every 2 points. If I take these 2 points on the horizontal component, draw a straight line between them, then all those points are on the curve, right? So it's convex, but not strictly convex. To be strictly convex, it has to be strictly above the curve, right? To be convex, it could be on or above. So this is convex, right, but not strictly convex. Cobb-Douglas is strictly convex. No matter what 2 points you pick, the points on the line in between those 2 points are strictly above the curve. Okay? A couple of things about this. One thing I want to mention to you, in some sense, you can see perfect substitutes and perfect complements are sort of the extremes for convex functions, right? Most of your convex functions are going to be somewhere in between. Okay? So the perfect substitutes, a linear line, perfect complements is extremely convex in that sense, whereas this is in between, right? So the nice thing about Cobb-Douglas is by varying the exponent, the alpha term, instead of being 2/5, 3/5, maybe we can make a 4/5, 1/5, or 1/9, 8/9. By varying that, we can vary the shape of this to make it closer to perfect complements or closer to a straight line, perfect substitutes. Right? So in some sense, the Cobb-Douglas can incorporate these 2 cases as extremes. Right? If you make alpha go, the exponent on x get higher, let me think about that. Let me think. I hold that. I'm not sure about that. I have to think that over. Okay. The second thing I want to point out is the reason we like Cobb-Douglas. Because it's strictly convex, it's going to turn out that it's going to be an easily differentiable function. Okay, so when we want to talk about choice, it's going to be very nice if we have a nice, smooth, strictly convex function here, as we're going to see. It's going to be easy to find what the consumer is going to choose. And not only that, because it's strictly convex, we know they can only choose 1 point. Let me give you an example. Well, we're going to see choice later on. But you may have right? You may have a function that looks like this. Try my pen. How about something like this? There. Yeah. I'm getting there. Okay. And there. Those are supposed to be 3 straight lines. Right? This is a convex function, but not strictly convex. That is, if I take 2 points on the same line segment, the points in between are on the line, not strictly above it, right? But any 2 points you pick on this line will be either on or above the curve. So it's a convex function, but it's not always above the curve, so it's not strictly convex. The problem with convex rather than strictly convex, and I'll get to this later in the course when we go to do choice, is that it may be that you get more than one solution for choice. All right? With strictly convex, you're only going to get one solution. So that's why we tend to use Cobb-Douglas a lot. Anyways, we'll see that coming up. All right. Okay. All right, any questions about that?
So if we say that we have multiple solutions on the convex curve.
What's that?
If we have multiple solutions on the convex curve, that's what we said, right?
Yeah.
So is the optimum solution the point where all 3 curves meet?
Well, I'm saying that what we're going to do next is we're going to say these are what you like, and now we're going to introduce what you can afford. The combination of 2 is going to determine what you choose. Now, it's going to turn out that if you have a convex function like that, it's possible that you could say I'm indifferent between a bunch of points, right? I don't care if I have, 6 pizzas in 4 movies or 4 pizzas in 6 movies. That's possible if you have a convex function. With a strictly convex function, it's always going to give you one solution, right? And that's nice, okay? Yeah, so we'll see that come up. Okay. All right, any others?
I might have missed something here, but I'm wondering what the theoretical significance is of like a concave indifference.
Right. So I showed this last class, just to show again. So one of the things about a concave indifference curve,
I think more specifically, I'm wondering why we're not don't care about the extreme like idea.
yeah. So a concave indifference curve, right? So if you take a look, draw up, you know, here's 2 points on the indifference curve, draw a straight line between them, all the points in between lie below the curve, therefore it's strictly concave, right? The consequence of that is it says you prefer extremes, the endpoints here, to the bundle in between. Because remember, every bundle below the indifference curve is less preferred, right? So if you have concave indifference curves, it's perfectly valid. It satisfies those three assumptions of monotonicity, completeness, and transitivity, right? So you can have these kind of preferences, but there's two things about them. One is it means that you prefer extremes to averages, and most people, at least at a broad enough definition of goods, prefer averages to extremes. Most people say, I don't spend all my money on food, right? Or I don't spend all my money on entertainment. I tend to spend a bit of both, right? So as long as you define the category broad enough, we do tend to spend an average of every type of good, all right? We tend to spend money on transportation, on our cars, say. We tend to spend money on accommodations, housing. We spend money on food. We spend money on entertainment. So we do tend to prefer averages to extremes. Doesn't have to be that case. You could be extreme, that's perfectly fine, right? The other reason I will say you prefer convex is the following reason. We said with convex indifference curves, notice that the margin rate of substitution gets smaller as you move down the curve, right? Remember, margin rate of substitution is the negative of the slope. The slope is getting flatter as you're moving down the curve. That says you're willing to give up less Y, less pizzas, to get another unit of another movie. Now think about why that makes intuitive sense, right? Up here, these bundles on the indifference curve, you have lots of pizzas and you don't have very many movies. So it makes sense that you're willing to give up lots of pizzas to get another movie, right? You say, listen, I'm swimming in pizzas. Here, take 5 boxes, just give me a movie, right? So you're willing to give up lots of pizzas to get another movie here. And that's indicated by the steep slope, a high margin rate of substitution. Down here, it's the opposite story. You got a whole bunch of movies, but you're hungry. You don't have very many pizzas. So you're saying, here's 12 movies I have. Give me a box of pizza or whatever, right? So here, you're not willing to give up very many pizzas to get another movie because you say, I already got lots of movies and I don't have a lot of pizzas, right? And that's indicated by the flat slope, saying you have a low margin rate of substitution. You're not willing to give up a lot of pizzas to get another movie, right? So that seems to make intuitive sense. If you have a lot of the good, you should be willing to give up a fair bit of it to get something you don't have a lot of, and then vice versa. Whereas if you have concave, it's the opposite, right? The slope becomes steeper as you move down the curve, right? So it starts out flat. That says you're not willing to give up very many pizzas to get another movie, low margin rate of substitution. And then as you move down a concave function, it becomes steeper, and it says, oh, I have lots of movies. That means I want to give up lots more pizzas to get another movie. That seems kind of weird, all right? So it's perfectly valid, but it doesn't seem to accord with what we see in the real world, right? So that's why we tend to pick convex rather than concave. It tends to make more psychological sense, okay? Good. Any other questions?
What is the significance of the cow, the one that says the X to the cow to
2/5? Okay.
what's the significance of it? So,
Of the power, the actual number?
no, I mean like in modeling the utility function. So for instance, the first two graphs, the perfect complement is the X at the same
Yeah.
time. So why are we
So I showed you the diagram. This one's somewhere in between.
yeah, so what do you use it for?
Okay, so the nice thing of it is by varying the power, it's still summed up to 1, but instead of being 2/5, 1/5, maybe we can make it 1/10, 9/10, or 9/10, 1/10. By varying that, we call that the taste parameter, right? By varying that, we can vary the shape of the curve and make it more like perfect complements or more like perfect substitutes. So it allows us to give a range without imposing one or the other. We can, remember, it's somewhere in between. Okay, it's somewhere in between. By varying the power, right, we can vary the shape of this to make it more curved, right, more convex, or flatter, right? So we can make it closer to perfect substitutes or closer to perfect complements just by changing the exponent.
So are there any examples of where you would use this to model the are there any examples of like
Yeah, so well, in some sense, most examples are like this because we said that Cobb-Douglas gives us this nice convex indifference curve, right? So what it's giving us is saying we prefer averages over extremes, right? And that's what most decisions we do. I said you spend some money, your budget on food, you spend some on entertainment, some on housing. Yeah, so it gives us a convex indifference curve, which is what we tend to see in the real world. Okay? Yes, and it's also very easy to work with, which is why we use it. There's more realistic ones, but they're harder to work with. Okay? All right, are we out of time? All right. I will try to post you tutorial questions tomorrow. All right? Best of luck. Have a good weekend. If you don't want to be on famous, you should stop the recording.